But then Ulam had a flash of insight. What if I just play hundreds of games and count how many could be won? That would give him some sort of statistical approximation of the answer. Back at Los Alamos, the remaining scientists grappled with much harder problems than solitaire, like figuring out how neutrons behave inside a nuclear core. In a nuclear core, there are trillions and trillions of neutrons all interacting with their surroundings. So the number of possible outcomes is immense, and computing it directly seemed impossible.
But when Ulam returned to work, he had a sudden revelation. What if we could simulate these systems by generating lots of random outcomes, like I did with solitaire? He shared this idea with von Neumann, who immediately recognized its power, but also spotted a key problem.
See, in solitaire, each game is independent. How the cards are dealt in one game have no effect on the next. But neutrons aren't like that. A neutron's behavior depends on where it is and what it has done before. So you couldn't just sample random outcomes like in solitaire. Instead, you needed to model a whole chain of events, where each step influenced the next. What von Neumann realized is that you needed a Markov chain. So they made one, and a much simplified version of it works something like this. Now, the starting state is just a neutron traveling through the core. And from there, three things can happen. It can scatter off an atom and keep traveling, so that gives you an arrow going back to itself. It can leave the system or get absorbed by a non-fissile material, in which case it no longer takes part in the chain reaction, and so